Okay, this is the video for lesson 1.2 on analyzing graphs of functions. So we're just going to jump right into examples here and look at different aspects of functions. So I have an advertising example that gives us a function f of x equals negative 5x squared plus 50x that approximates the profit of a toy company where x represents marketing costs and f of x represents the profit. Both cost and profit are measured in tens of thousands of dollars. We're going to use the graph to estimate the profit when marketing costs are $30,000. So when looking at the graph here, on the bottom I have marketing costs are labeled and they're going up by tens of thousands of dollars. And then the profit is going up by tens of thousands of dollars also. So when they're asking me to estimate the profit when marketing is $30,000, I'm not actually looking at 30,000 or looking for the number 30,000 on this graph. I'm going to go to 3 on the x and then go straight up and find out what this y value is right here. Okay, so I'm going to then confirm this algebraically by plugging in 3 into this function, not 30,000. It's because 3 represents $30,000. So over to the side here, I'm going to do f of 3, and I'm going to plug that into my function. So f of 3 is going to equal negative 5 times 3 squared. I'm going to run out of room. Plus 50 times 3. Okay, so I'm going to type that in my calculator. I know that 3 squared is 9 times negative 5 is going to be negative 45. And then 3 times 50 is going to be positive 150. Running out of room. So then 150 minus 45 is going to equal 105. Now going back to this problem, remember this represents tens of thousands of dollars. So if I do 105 times 10,000, we're going to get that our profit, and I'm going to write this out to the side over here, that our profit, my pen's not really working with me, is actually going to be $1,050,000. So what this means, if I spend $30,000 in marketing, and that could be advertising of some sort, then I'm going to make a profit of just a little over $1 million. Now you can see on this graph that just because you spend more money on marketing doesn't necessarily mean you're going to make an infinite amount of profit. There's definitely a spot on this graph where you maximize your marketing and you maximize your profit. So if you think about it this way, if I just advertised out the wazoo and you saw a commercial all the time about a product, that's going to make you get annoyed with that product and you're not going to want to buy it anymore. So there's definitely a spot where you can spend this amount of money and that's where you're going to make your most profit. Okay? So evaluating a function, you should be able to plug into that function value and confirm it algebraically and graphically. Okay, on this next example, we're going to be looking at the domain and range of this function. So remember, domain goes with the x values, and the range goes with the y. Okay, so we're going to be looking first off left to right and see how far this graph goes left to right. Well, I can see that there's an arrow down here at the bottom, and it's going to keep going down. As the graph is going down, it's actually going to be going further and further to the left. So for the domain then, the farthest left that this graph is going to go is actually going to be negative infinity, because the further down, the further left it's going to go. And then I can see that this graph actually stops over here on the right hand side because it has that point instead of an arrow, and that's at 3. So it goes from negative infinity to 3, and since it actually equals 3, that's where we're going to use the bracket. Okay, so this is that interval notation that we learned about in section 1. Okay, same thing for the y's. I already talked about that the graph is going to keep going down forever, so same thing for the range. We're going to start out at negative infinity, and then I want to see how far up it goes. Well, I can see that the highest it goes is right here, which is 2. So 2, and again, it does actually equal 2. So I'll go from negative infinity to 2 on the range. Okay, number 3 wants us to use the graph of this function to approximate the y-intercept and then show that algebraically as well. So remember, the y-intercept is where it crosses the y-axis. So I look at my graph and I'm looking for where it crosses the y-axis, and I believe that's about right here. So I would say that graphically the y-intercept is at the point 0, 4. Okay, now they want us to confirm that algebraically. So the y-intercept is always going to be when x equals 0. So if I plug in f of 0 into this function, so that would be 0 squared minus 4 times 0 plus 4. Okay, I can see that all of that's going to zero out except for that 4 on the end. So f of 0 actually equals 4. So same thing, my y-intercept is actually at the ordered pair 0, 4. Okay, example 4 wants us to approximate the zeros of this function. So zeros of a function are where it touches the x-axis. So a lot of times we use the word zeros, solutions, roots. All of those mean the same thing. So we're looking at these points on the graph that it touches the x-axis, and this one actually has 3 points. So I'm going to write those out. So I've got the point negative 1, 0, 0, 0, and the point positive 1, 0. So graphically I can see what those 3 points are. Now we need to do it algebraically. So algebraically is when y equals 0. And remember, y and f of x are the same thing. So if I plug in 0 in place of f of x equals x cubed minus x. And I want to solve this problem for x. First thing I notice is that both of these terms have something in common. And what they have in common is an x. So I can factor in x out of both of these terms. When I factor in x out, I'll be left with x squared and then minus 1. When you factor and you have two things that multiply to equal 0, you can actually separate those two things. So 0 equals x is one solution, and 0 equals x squared minus 1 is another solution. So I can continue solving. Well, the x equals 0 is one solution. I already have that. Now for the other one, I would add 1 to both sides. So now this is going to be 1 equals x squared. And remember, to cancel out a square, we take the square root of both sides. And so whenever you take the square root of something, remember it's always the positive and negative square root of that number. Well, the square root of 1 is just 1, but this is going to give us two solutions. This is going to give us positive and negative 1. So that's our three solutions that we actually got graphically as well. 0, negative 1, and positive 1. Okay, when we're looking for symmetry, here's a lot of information. Most of the time, if you're looking at a graph, you can tell where it's symmetric. So a graph is symmetric to the x-axis if you could fold it across the x-axis and it matches up. Okay, with x-axis symmetry, you're going to have x's that repeat and maybe have two different y values. So that's why a graph that is symmetric to the x-axis is actually not a function. Okay, if it's symmetric to the y-axis, we can fold it in half vertically and will match up. And so that actually means that the y values repeat. I might have two different x values that are the same number but opposite sign, and then the exact same y value. And then origin symmetry is a little different. Origin symmetry is actually symmetric across the line y equals x. And so you could replace x with negative x and y with negative y, and you would get a equivalent equation. Okay? And then last thing, determining if a function is even or odd. So a function is called even when it is symmetric to the y-axis. A function is odd when it is symmetric to the origin. So the way to do that algebraically is if you plug in a negative x in place of all of the x's, and when you simplify, if you get the exact same equation as the original function, then it is called an even function. If you plug in that negative x and simplify, and you actually have a complete opposite function, everything changed signs, then it is an odd function. If when you plug it in, it does all kinds of crazy stuff and it's either not exactly the same or completely opposite, then it is not even and it's not odd, so we just say it's neither. Okay, so let's look at an example of that. Here's number 5. It says graph the function x squared minus 4x plus 4, and this is a screenshot from the calculator. It says analyze the graph and determine whether it is even, odd, or neither. So I can actually look at this graph and I can see that it's not symmetric to the y-axis. I couldn't fold it across the y-axis. It's not symmetric across the x-axis. It's the origin part that may be a little fishy. Okay? So I'm going to show you algebraically what we need to do. So in place of all of the x's, I'm going to plug in a negative x. Excuse me. So I'm going to put negative x squared minus 4 times negative x plus 4. And I'm going to simplify as much as I can. So a negative x squared is going to be a positive x squared, because a negative times a negative is a positive. When I do negative 4 times negative x, that's going to be positive 4x. And then at the very end, I still have a plus 4. So first thing, is this function exactly the same as the original function? No, it's not. So it's not an even function. Next thing, is it completely opposite of the original function? Are all of the signs different? And no, it's not. If all of the signs were completely different, it would be odd. Since there's just a whole mishmash of things going, it's neither odd nor even. We're just going to say this is neither. And so since it's neither, it's not, doesn't have any type of symmetry that we've talked about.